we are capturing this audio. All right, so back to what we were doing. Homework 5 retrospective. Of the people that attempted it, 22 managed to raise their course grade, which is great. And based on people that didn't log in for the last homework or this homework, I'm guessing that we are waiting on about 12 to withdraw, meaning we have like 65 people in the course. Based on the numbers I see, I think that's about accurate.
Can you actually see the link to the slides for a moment?
Yes. Link to the slides. I should have that link on every slide. That would be useful. Maybe on the top left there.
Or you posted it college.
Or that, yeah. Exactly. That's also that's a brilliant idea. That's like pre-caching. All right, everyone got the link? Brilliant. All right, so I think we'll finish out the semester probably with around 30 people. Or 30. Hopefully not, around 60 people. I think that'll be great, and you'll be 60 super expert hackers. The student grade distribution, the idea of this course was, of course, to kind of help, of this homework was to help people that needed those walkthrough challenges a little more. And I think that worked. So this is the distribution before. This is the distribution after. Of course, the scale is a bit broken because I won't go into it. Basically, Linux is a piece of crap sometimes. But you can see this before. We kind of upped the number of Bs, upped the number of... actually, we pushed a lot of Cs into Bs, a lot of Ds into Cs, and so on. And the people that are really, that were in the 20s, 30s, and so on have been kind of pushed to the right a bit. So this is something I'm a lot happier with. In terms of a new scoring system, I didn't have time to look into it, but I will continue to dream about a new scoring system. Any scoring system changes will be on an opt-in basis. It'll come up with a new scoring system, and then you can opt in or not opt in, depending on what's better for you. But honestly, I think this scoring system is not the worst. Anyways, cool. So, a couple of things I want your feedback on. One is, do you like having SSH back? Did it help? Okay. All right. So we'll keep SSH around. SSH makes it a little harder for us to record all your traffic, but we figured out workarounds. So now we can, and by we I mean Connor, will soon begin to record all of your traffic again. So don't use any passwords and so forth on these connections that you don't want immortalized. The other question is, how were the walkthroughs? So if you found the walkthroughs helpful, and only 26 people did the homework, of course, but if you found it helpful, I mean, it be a show of hands. Okay, did anyone get from like not understanding at all to a good understanding with walkthroughs? Okay, awesome, brilliant. All right, so I'm happy to say the walkthroughs are here to stay. They do make the homework significantly longer to write. So as probably a pattern that we'll see is, you know, the first night we have walkthroughs ready for like half of the assignments, and then we get more and more put up over time. That's definitely the pattern for this homework. All right. Any other questions, concerns about anything? Homework, class, exploitation, reverse engineering. Cool. Okay. Let's move on. This week, we are going to talk about shellcode and shellcode injection. This is a topic that is near and dear to my heart. It's probably my favorite part of the exploitation process. It's a little more rare nowadays, as we'll discuss, but I love writing shellcode. I love getting around various constraints on my shellcode and so on. And your homework this week will really force a lot of this, my view on shellcode, onto you, hopefully. All right. So the story so far is that in homeworks 4 and 5, we mostly did these attacks that would either overwrite data that wasn't very important, or redirect execution to a function that would just give us the flag, and so forth, right? And in all of the cases, there was either a handy win function that did what we wanted the program to do, and we would trigger that win function. Or even if we couldn't directly trigger the win function, there was some sort of a win variable that, when proper conditions were achieved, would cause the program to trigger the win function. That's nice as an introduction to memory corruption, but it's not frequently the real case when you're actually exploiting stuff. Sometimes there is no win function. So let's have a very quick review, just so we don't forget it, of what memory corruption is like, and then we'll move on to shellcoding. The basic idea is our programs start up with some amount of memory that is already influenced by the user, right? So you can see over here, program starts up, text is kind of clean, it's all program code, the heap, all program stuff. The stack has some user-controlled data. Why? What is controlled by the user on the stack when the program starts up?
Environment variables?
Environment variables. That's one thing, right? So you can control, depending on the situation, but let's say in these homework assignments, so far you control the environment. What else do you control? I'm sorry?
Command line arguments.
Command line arguments, exactly. You control the environment variable and command line arguments. And so those are already user controlled, and then the program starts to run. And as the program executes, user data will just kind of spread through the program, and more user data will be read into the program, and so on. And normally, user data doesn't directly control program execution, right? Your user data shouldn't directly mandate where the program will jump, or directly determine what the program will execute. But on modern systems, as you've observed in your in homework 4 and homework 5, this data, user data, is often stored in the same places as very critical control data used by the program. And so here we can just kind of see graphically, there's user data on the heap and stack, and then there's control data being stored there as well, and being used for different things. What you've done in homework 4 and 5 is trigger some sort of a memory corruption, some sort of buffer overflow or whatnot, to spread your user-controlled data over data that shouldn't be user-controlled, right? So the return address or the win variable, right? And if you overwrite some data that is used by the program to influence its control flow, then, like a return address, you can redirect execution to a win function, right? And that's what you did in many, many ways in homeworks 4 and 5. The interesting thing that we'll talk about in this class is you can also redirect it into your own code, right? Because you control the address. Let's say you control fully the address where the program will return to, where the function will return to. You can redirect it into data that you have injected into the program, which will then be executed as code, with many caveats that we'll talk about. So that's kind of the general overview for the day. Let's talk about, given this memory corruption, what what kind of things can corrupt, right? And so we already mentioned that you can corrupt this number 2 thing. You use this in the homework. You can corrupt a win variable that is then used to influence indirectly program behavior. But basically, you can corrupt any sort of a standard value. You might be able to, depending on what the bug is. Number 3, you can corrupt a pointer that is used to read data. So some area in memory that's normally stores a pointer that you overwrite, and now you control the memory that the program can read. You can overwrite a pointer that is used to write data, or you can overwrite a pointer that is used to execute data. And so far, you have done number 2 and number 5, right? You have modified the win variable, and you have modified the return address directly. Cool, and you have, in homework 4, there are a couple of unintended situations where you were modifying a read pointer, which could cause the program to then crash if it accessed it again, right? And so, of course, with these situations, you have to be pretty careful. And generally, you take several different vulnerabilities or the same vulnerability in different contexts, and you accomplish a number of memory corruptions leading to some goal, where you either modify the win variable, redirect control to the win function, or inject code. So how does this relate to the real world? In the real world, code injection has been around for almost as long as buffer overflows in general. Or at least it has been documented for exactly as long as buffer overflows. So if you mentioned 2 classes ago that the first documented buffer overflow was the Morse worm that brought down the internet in 1988, right? The Morse worm overflowed a stack buffer in the finger D service, and there was no handy win function in finger D, right? So Morris injected his own win function, which essentially would set up, and this is kind of the equivalent in AMD 64, shellcode would set up and execute /bin/sh so that he could take control of the remote server. Okay, so why is this possible? This is possible because of these 3 gentlemen. You might have heard of them, or remember them rather, from a couple classes back. I think week 3. These are the 3 Johns that brought us the von Neumann architecture. Of course, von Neumann is the John on the right over there. And in the von Neumann architecture, data and code is the same thing. They're treated exactly the same for the most part, right? This is in contrast to a Harvard architecture, where you have one area where you put data, one area where you put code, and in the traditional Harvard architecture, never the two shall meet. In the von Neumann architecture, code and data are stored all together, jumbled up, same memory, space, and so on. And almost all the computers that we consciously use are von Neumann architectures. Your laptops, the main processor of your phone. Where's my phone? My phone's over there. Servers and so on. Von Neumann architectures. A lot of embedded devices. Some of the basebands on your phone, depending on who created them. A lot of the little door scanners that you use to get into various buildings around here. Arduinos, they tend to be more frequently than general computers. They tend to be Harvard architectures. There are various reasons, architectural reasons, behind that shift and behind why everyone uses von Neumann architecture for the most part, that we're not going to go into from the perspective of hacking. But what we will have a quick discussion about is what is the problem security-wise with von Neumann architecture's tendency to view code and data as equivalent. So, any ideas?
Can you just start inserting code into the thing using the same methods that you use to override data?
Yeah. So, for example, if it treats data and code equivalently, and we'll go into this concept, of course, throughout this lecture. If data and code are the same as you write data into the program, because of course you write data into the program, it's very close to writing code into the program, right? In a true, von Neumann, a vintage von Neumann architecture, nope. In a vintage von Neumann architecture, there is no difference at all between code and data, right? So if you can trick the program into executing your data, you're executing code. In a true Harvard architecture, this wouldn't be possible because they're very separate. Realistically speaking, modern Harvard architectures are not pure Harvard architecture. They allow for the modification of data, of code. So that means accessing code as if it was data. And modern von Neumann architectures, as you'll hear, have some security measures because it turns out it's crazy to just treat all data as code anyways. But that's kind of the core problem. Can anyone think of any other problem? Any other problems? No other problems? There's something called the von Neumann bottleneck. This has nothing to do with security. The basic idea is if your code just lives in memory the same as data does, then you tend to read code using the same pipeline that you read data. And so they compete for resources. So if you have a lot of code that you want to execute on a lot of data, then you are constantly reading both the code and the data, and things are slower. So you get around that by caching a lot of it.
Is that why Spectre meltdown before Shadow worked?
Yes. So there are these measures to get around these performance problems. And these measures basically encompass the concept of adding caches. And so anytime that you access memory, that takes some time. You say, I want to access byte OX1000. The CPU says this. The memory controller says, OK, hold on. And the CPU has to sit and wait while byte OX1000 is accessed. Right? And then next, the CPU is going to say, OK, now I want to access OX1001. And then it waits until 1001 is accessed. And then it says, I want to access 1002. And then it waits. Right? And so what people very quickly realize is, hey, if you access some amount of, if you access some memory location, it's likely that you'll access memory locations around it, right? The most common operations that we have tend to be operating on the same data that is, located close together in memory. So what happens nowadays is when the CPU says, hey, I want to read byte OX1000, that entire page, and you now know, you all remember what is a page in memory, right? How big is a page in memory? Say most modern systems will say x86 default. 4K. OX 1000 bytes. You have big pages. So you can have very large pages, but at the very least, that one page is pulled into the cache, depending on your specific, how your specific cache works, maybe more. Wait, is that true? It's not quite true. Anyways, the point is a bunch of data gets pulled into cache, and now it is in a fast access area right next to the CPU, and now things are faster, right? So the next time when you access OX1000, the entire page, let's say, or some part of that page gets pulled in. When you access OX1001, things go very fast. Cool, right? So that is step one. Step two is this brilliant idea that, hey, what if we actually look ahead in memory and in the code, and we try to predict what the CPU will execute next, and whenever there's no memory traffic, we just pre-cache it. Right? We try to fetch that into our cache ahead of time. And now you have Spectre. Because now you can say, okay, let's make it look like we're about to access let's make it look like we're about to access. It's a bit complicated. Let's make it look like we're about to use some piece of memory to dereference some other piece of memory. The pre-cache process will then say, oh, it looks like you're about to use memory in this way. It loads some stuff in the cache. And then you can use a timing attack to see what is in the cache, because what's in the cache will be much faster to load. And based on the results of that, you can predict what was in the piece of memory that you didn't have access to. Did any of that make sense to anybody?
Does that exploit still exist? Yes.
Yes, it does. So publicly, there are, I'm not sure if there are no, to my knowledge, publicly available exploitable Spectre variants extant right now, but I can guarantee you with 100% certainty that there are private Spectre variants exploitable on latest kernels right now. So it's a big problem, and it hasn't been solved. The only surefire way to solve it is to turn off this pre-caching behavior, but then you lose something like 25% of your performance, something insane. But yes, so a lot of them exist. Some of my students can actively leak kernel memory on fully patched machines. It's pretty crazy stuff. Is that something that people would be interested in as a class? Like as a of 1 week of this course? Could try to work that in. I'll try to think what to swap out. And also,
Nobody needs.
I have to think of how to make challenge sets for that. That'll be interesting. Cool. Okay. Problem if you. What are some of the benefits of viewing code as data? Why did von Neumann take over the world?
Seeing it easier.
Yeah, it's a lot easier. You don't have to think, how big is the code going to be? How big is the data going to be? On a true Harvard architecture, let's say you go all the way and you have literally two different, memory, like hardware memory modules. You might run out of one or the other. You can, it lends itself very nicely to our caching model with memory, where you can have, depending on how big the program is, you might cache the whole thing. You could cache less of it, more of it, and so on. And it, go ahead.
Self-modifying code is possible. I don't think it's possible.
With a pure Harvard architecture, you can't self-modify code, and that's probably the biggest relevant one today. Modern Harvard architectures are what's called modified Harvard. So on AVR and PIC, realistically, you can self-modify code. You can say, I'm going to redeclare this code as data, which is very similar to what we do nowadays on von Neumann architectures, and then you can modify it. But traditionally, you couldn't. What's the case where you might want to modify code during runtime?
Self-patching.
Self-patching is one. But can anyone think?
There are a lot of optimizations you can make. Like if you have a check that only needs to be run once in a loop, you can patch it out.
Okay. What situation would that be frequently done? There is one. You all do it billions, maybe trillions of times a day on your computers. What's a case where you would want to self-modify code, and then one case was you could optimize essentially code at runtime. You see that some check is absent, and then or some check is useless, and you remove it.
Does that mean that machine learning isn't doable on Harvard architecture?
No, machine learning essentially, let's say a neural network, you train your bunch of neurons,
Right.
which is all data, and then you have whatever your actual classifier execution thing is. You don't execute the neurons directly.
That's
You
right.
execute a program that uses them as data.
Anytime you do anything, it's self-learning. It's gonna load code from somewhere in memory and have it all in memory always.
Yeah. Excuse me. I tried to talk and drink at the same time. Yes, that's one. That's a very real situation, and I think it would be, of course, tougher in some sense. I guess what Matt is saying is, when you download it off the internet, there is no distinction between code and data, right? You don't have a different internet for code and a different internet for data. If you were a true Harvard architecture purist, you would have two internets, and one just has code on it somehow, one has data, and the two don't touch. We obviously don't have that. I don't even know how that would work. So already, if you go abstract enough, we assume a Harvard von Neumann architecture somewhere. So that's a very good point. But there is somewhere in your computer where multiple times a day, probably since this class started, trillions of times you have modified code.
Just-in-time compiler?
Just-in-time compilers. So nowadays, all major browsers, all browsers, I would say, even let's say minor ones like Edge or something, all browsers compile their JavaScript as they run, right? So they start out interpreting it, then they notice, okay, this piece of code runs very, very frequently. Let's do an expensive compilation step with a lot of optimizations, stuff it into memory, and then we start executing that. And then even more so, the standard approach, and this gets a little out of the scope of security as well, but JIT itself is not. We'll talk about it in a second. The standard approach is first you do a light pass to recompile, to compile it just into, without many optimizations, and then you realize, oh, I am actually executing it a lot. Then you recompile it with more optimizations and so on. So you're modifying code quite a bit. And it's not just JavaScript and browsers. Java does this. Python does this. You use PyPy. Lua does this. A number of other architectures do the same thing as well, or other languages. Cool. So, of course, in order to do that, you need to, in some sense, view code and data as kind of semi-equivalent. And in summary, von Neumann for the win. So, what is shellcode, and why do we call it shellcode? We've now very much determined why we have this architecture that allows us to inject code. Why do we call injectable code shellcode? Of course, usually the goal of an exploit is to give you arbitrary code execution. Easiest way of this, usually, not always, easiest way to do this is to launch a shell, such as /bin/sh, and thus the term shellcode. Cool? Any questions about the term shellcode? Imagine if the goal was like always to shut down a remote machine. We'd be calling it halt code. That'd be interesting. But it's shellcode. So, we're going to go through shellcode injection from step 0, how to inject shellcode, through all the way to reaping the benefits. Step 0, how to inject, it depends on the program, right? You might have a situation where you can control a right pointer, and using that right pointer, you can set values in memory to be equal to your shellcode. You might have the buffer overflow case, where you just you overflow the buffer, and in that buffer you leave your shellcode. We'll discuss why this is tricky. There are a ton of different cases of how to inject. and how to inject and where to inject are just kind of two combined to cover them separately. So we're going to cover them together. But there is a conceptual difference, right? One is, what is the vulnerability that gives you the control over the program you need to inject your code? And two is, where do you want to put your code? Generally speaking, the vulnerability mandates where to put it anyways. So we'll cover it together. So traditionally, you could inject your code anywhere. In a traditional von Neumann architecture, and this is only true going really far back, you could write code, you could write data, jump to that data, and the computer would kind of blindly execute it as code. This is what Morris used. Again, Morris overrode a stack buffer, redirected the return address into that stack buffer, and brought down the entire internet. And this persisted for 20 years until like 2010. 2010, we started seeing these countermeasures against this specific thing. For one thing, canaries became commonplace. So,
When did NX become a thing that was widespread?
widespread also around 2010.
Really?
Yeah,
That late?
that late. Very late. Yeah, so I remember I was already in graduate school, so this would have been 2010. We were playing a CTF, and on the hardest difficulty exploitable challenge, they had canaries and NX enabled.
Wait, that was the difficulty.
That was the highest difficulty exploitable challenge. And we pinged the organizers, and we said, hey guys, do you know that you forgot to disable canaries and NX? Like, oh shit, sorry about that, and they fixed it.
Are you
They
kidding?
turned it off. I mean, that's how recent we actually started taking memory corruption seriously. I mean,
Just out of curiosity, in DEF CON in 2019, if we ping you and tell you that you forgot to disable NX,
no. In 2019, if you don't have a challenge, if you have a challenge without NX, it's a learning challenge, like in the homework.
Couldn't you make NX
Don't you bump shellcode challenges?
so hard
I-
that they couldn't do it?
Yeah, you could. I mean, there's,
There's a challenge.
generally speaking, I'll get to all the questions. Generally speaking, self-respecting challenge writers, rather than turn off NX, they just map an executable buffer in memory somewhere else. Because turning off NX, there was another question. So,
Maybe I'm out of the loop. What do you mean by NX?
sorry, we're about to get to that. I apologize. It's the next slide, actually. So, this style of buffer overflow where you go past the frame, you override the return address, and then you jump into your own buffer. It's kind of the traditional stack-based interframe buffer overflow exploit. Probably it's the most impactful memory corruption vulnerability in history. Probably one of the top 3 most impactful vulnerabilities, period. Probably behind SQL injection and cross-site scripting. But it's a huge, huge deal. Aside from bringing down the internet in 1988 with the Morris worm, it was responsible for the Slammer worm. How many of you guys were alive when the Slammer worm hit? It'd be 2003, I think.
I think we were all alive.
All alive. Sentient?
no.
Company had a computer.
Yeah.
15-year-olds here?
The Slammer worm, it hit when I was in high school. The Blaster worm, I think it also used a stack-based buffer overflow. You can find a list, actually, of high-profile buffer overflows on Wikipedia, if you're interested. Blaster hit when I was in college, if I remember correctly, and I actually ditched work because I was working at a help desk. And I said, fuck this, I'm out sick today. And so on. And up to, more recently, has anyone hacked their Wii with the Twilight Princess hack? No, I expected more. Has anyone hacked their Wii with anything?
Console gaming? Come on.
Yeah. All right. Anyways,
That is the correct response, by the way.
I don't know if you all know, but Nintendo once released a console called the Wii. It had a number of vulnerabilities in various games and so on that could be triggered by modified save data. One of these was in Twilight Princess, where if your character's name was too long, it would copy it onto the stack, and it would overflow. And it would cause an interframe stack-based buffer overflow that would allow you to take over the system on the Wii.
That's really recent.
I mean, these things are still occur. Of course, modern systems have more and more mitigations, and so we'll talk now about the NX bit, which stands for no execute. And so eventually, even the von Neumann followers realized that we just can't have this shit where you can just write a bunch of data and suddenly you are executing code. And so architectures, processors have supported memory permissions for a long time. Nowadays, they're actually very thoroughly used and very thoroughly what's the term? Enforced. And we've covered this before, right? Read, write, and execute protected memory. It's the exact same thing as on your in the file system. You have read, write, and execute permissions. If we start up a sleep, for example, and then we look at, actually, let's start this up in the background since this one is logged. We look here, and we'll do just this. So here's the memory map of sleep. We have the sleep binary itself being mapped here. Why is it a weird 5.5 address? ASLR, and position independent code gets mapped to 5.5. What is 5.5 in ASCII? No, that's 4.5. 5.5 is capital U. I don't know. I was hoping it was a P and then it would make sense, but. Oh, who said you? You said you from memory? Good job. Amazing. I'm sorry I didn't hear you. I should give out like extra credit for these sort of things.
Starting today.
Exactly. This just occurred to me. All right.
You got extra credit for asking good questions.
Yeah, that's not a bad idea either. Okay. So, and you can see everything mapped by the memory by the program has some permissions. So we have the program itself, and we've gone over this when we were talking about binary files in like class 1 or 2, right? We have the code segment, which is executable, read-only data, which is just readable, and the global variables, which are readable and writable, right? And the program itself, that L file, is distributed into these three things. Everything else, libraries have the same thing. They're object files, just like your program. Read executable for the code. Then there is a page with no permissions for whatever reason. Often guard pages are used to protect other parts of memory, so you can't just read from one area all the way through and into some sensitive data. I doubt that's what's happening here, but it could be. Just other pieces of memory. So basically, modern architectures support memory permissions, and the intuition that someone realized depressingly late, as Zach pointed out, is that normally all of the code in your program is located in the text segment. So you compile it, or the text section, you compile it, it all ends up in .text. Same with libraries, they all have their own .text. So there's no need to execute code anywhere else. You shouldn't be executing code anywhere but .text. And so by default, everywhere else, such as the stack, the heap, the read-only data, the global variables, and so forth, are not executable. And your shellcode needs to execute because it's code. And so that's it. Shellcode is over because you can't execute shellcode. So what are some underlying assumptions here that might be wrong?
We can't remap the memory?
We can remap memory. Oh, you mean
No,
that's the
because
assumption?
that's-
Exactly. One assumption is that you can't remap memory. What's the other assumption?
That executable pages aren't writable.
That executable pages are never writable.
Game over.
That is absolutely a. I'm not giving you extra credit for that one, but it's good. Right. So by default, the new paradigm is that if a page is executable, then the loader will make sure it's not writable. There are no pages here that are executable and writable. All right. What's a case where you absolutely need a writable and executable page? Yeah, we just talked about this. You need to be able to write to the same page as you execute. And we'll go into, there are a couple of different cases of JIT. And there are a couple thus different cases where you can write and then execute your code. So it's not over. Of course, NX has made it a lot more situational, a lot harder. Shellcoding is a dying art, unfortunately, and it's something that is very near and dear to my heart. I consider myself a shellcoder, but it is increasingly being forgotten. There's a lot of tooling and instrumentation around trying to ensure that people don't have to write shellcode, and in most cases it's sufficient. So even for your homework, you'll be able to use a lot of tools to help, but the homework will force you to get very proficient with the ancient art of shellcoding. So, what are some remaining injection points? So one that was mentioned is there's an assumption, or not an assumption, but it's not the case that once you take away write access, then the write access is gone to memory. You can remap memory as writable. And this is done in Linux with the mprotect system call. And so you can do one of two things. You can either trig the program. Whoa, nice catch. You can either trig the program into mprotecting some executable memory to be also writable, or you can trig the program to mprotect some writable memory to also be executable. There are some kernel extensions that will actually really angrily try to prevent you from doing this, but realistically, I mean, your browser has to do this, Python has to do this, this has to be supported. How do we do it? The most common way is through return-oriented programming, which is actually closer to what you did in homework 4 than what you'll be doing in this homework, right? It just involves rewriting return addresses, essentially. We'll cover that next week, along with some other advanced exploitation techniques. This week we will not. Other cases are more situational, depending on what the program is doing, right? So if you can overwrite the pointer, the memory pointer that is passed to mprotect for some other thing, then you might be able to force a program to mprotect some other piece of memory where your shellcode is, or where you can then write your shellcode, and these sort of things. So, one way to protect against this, if your program has absolutely no need to mprotect memory at all, if you're not a just-in-time compiler, and if you don't have any kind of unusual memory demands, then you can actually disallow and protect using a system called firewalling feature in the Linux kernel called seccomp. Not going to go into that, but there are solutions. You can also use that same thing to force mprotect to only be able to work on some specific location. If you, for example, are a just-in-time compiler, and you say, okay, all my just-in-time compiled code is going to be here.
You have an access to seccomp, but you can also just remove syscall and other things, but syscall, for example.
So you cannot. So seccomp runs after you call syscall, and I don't have a seccomp slide, but basically seccomp. I do have a seccomp man page. Seccomp. Well, that's.
I'm sorry, not syscall. The exec read syscall.
Yes, but you could still read, write, open, read, and write to get sensitive data, right? Even if you disable exec. So the question was, if you have a syscall firewall, can't you just say, okay, I don't care if I'm exploited, but I'm not going to allow people to launch code? That is the underlying concept of sandboxing, right? So you say, okay, no matter what happens, and this is used nowadays. So your browser, depending on what browser you run, if you're running Chrome, your sandbox, the code that is running in your pages, in your web pages, the JavaScript, it is just-in-time compiled down to binary code, executed as binary code, and in some sense, if an attacker abuses it, that functionality of just-in-time compilation, they could achieve arbitrary code execution on the binary level, on the native code level, right? And so, of course, this is much worse because JavaScript has a lot of built-in security protections. For example, it won't let you open random files in the file system. Once you have native code execution, you could just call syscalls, right? Getting to that level, if you have a bug like that, I can tell you that it's worth about $200,000 at least, maybe $400,000, depending on the terms of sale. But at that point, you're still running within Chrome's sandbox. So Chrome uses seccomp, and this man page isn't very useful. But basically, using seccomp, you can add filters that will run and filter out bad system call arguments, such as anything to exec, or making sure that the only files you can open are inside some directory that is safe to open, or something like that. If you have a bug to bypass seccomp, which means that you have a bug in the Linux kernel or in the seccomp rules that Google wrote for Chrome, now your bug is worth quite a bit more. I honestly have no idea how much. I wouldn't be surprised if it hits 1 million for the combination of end-to-end getting code execution inside the sandbox and escaping that sandbox. That's pretty rare nowadays. Fish, do you know how much that might be worth? Yeah. Probably quite a lot. So, seccomp is a layer on top of everything that we're talking about. Adds a little bit of extra protection, but we won't go into it today. But it is on the list of concepts. Sandboxing, very important concept in modern security. All right. Any other questions?
When you remove privileges from yourself, right? To remove access to someone's system, do you do it for just a range of addresses? Like if I'm executing this page, then I can't use the syscall. How does when the JavaScript is completed running, you return back to the other browser code? How do you regain privileges, or is it only upon forks?
It's on a per. So here I'm a little. It's either on a per thread or per process. I think per thread. To do it safely, you have to. It has to be a one-way operation. So you say these are the seccomp filter rules, and these will always be the seccomp filter rules until this process dies. And all the children will inherit these seccomp rules, and so on. And so you, in Chrome, you have this multi-process model, right? So you have your process that's running your page, and then you have a different process that actually runs the GUI, right? And so that different process is either not sandboxed at all or sandboxed more loosely. And your process that's running the page is sandboxed to hell. Does that answer your question? Awesome. All right. So that's method number one of re-achieving shellcode execution. You pull the program into protecting it, and then you start execution. And the lightsaber's back. Method number two, as we keep talking about, is JIT. There are two cases of just-in-time compilation caused shellcoding. Basically, the bottom line, as we discussed, these compilers have to frequently generate code, write it somewhere, and then have it executed. The safe thing to do would be to map the code writable, write it the first time around, and then remap it executable, execute it, and then when you want to update it again, remap it writable. So that's the safe thing to do, but not all JIT engines are safe. Why?
Not all do this. This vector memory, for example, the Dynamo is an actual sort of JIT to be used as a JIT, but it actually doesn't ever take away write permissions from the code. It's always writable and executable.
So most,
To perform it.
actually don't quote me on most, but I will say that anyways, most JIT engines, or at least many JIT engines, only do the first, well, not even just the first part. They just memory map, read, write, executable memory, and that's their JIT playground.
It's faster. Force and seal view.
There's a lot of caching, as we discussed von Neumann architectures, but also modern computing in general needs a shit ton of caching, and so you might flush a lot of this cache when you make different permissions. And as Zach said, it's faster, right? JIT is all about running stuff as fast as possible, right? So your JavaScript code, in order to reasonably run needs to be insanely fast. And so this is the solution is
Ignore safety.
ignore safety to focus on speed, to focus on usability. That's a common solution. What's another reason why actually this paradigm might be tricky? We just touched on it. The sandbox. So allowing your sandbox to call mprotect, there might be risks associated with that as well. In the worst case, you will be able to anyways mprotect stuff executable. So
But the sandbox code is
Yes.
the JIT code.
yeah,
And protect ones outside that. Right.
I don't know. If I had to guess, I honestly don't know. If I had to guess, I'd say the entire JIT engine runs inside the sandbox. Yeah. So, not all JIT engines are safe, and they, if they are unsafe, then we just had already this discussion, but most JIT engines don't bother mprotecting. If they don't mprotect, then we suddenly have a page in memory that is readable, writable, and executable. Actually, let's see Firefox.
Oh no.
Okay, let's. Did anyone use awk to leak a flag in homework 1? Nice, good job. All right, so we are here. Now we can do oh, sorry. All right. This gets us all of the processes running in my system. This graphs for Firefox. This prints the second column. It's an awk script that just prints the process ID. It's a very common thing that I type, and I should really alias it away. And this runs for each output of this. In parallel, it'll run this command. Right, so it's like xargs, but it's parallel. I can also say parallel-k, so it gives me the output in order.
For the specific curiosity, does that mean that it only passes only passes the arguments to the new line?
Yeah, so this is the argument, this is each line. It'll pass each line into the command. Parallel is super useful, and it's super good. Like, it'll handle cases of commands hanging. It does a lot of good stuff. There's also an extension of this called parallel-SSH that'll do all of this, but with different hosts over SSH. Very nice stuff. Okay, anyways, so let's grab for RWX. Oh, I guess not. So let's grab for X. So these are all of the executable pages, and they are all, none of them are read, write, and execute. Today I learned. Do I have Chrome on here? No. Chrome, Google Chrome? No. Down with Google. All right.
I should try Internet Explorer.
What's that?
Yes.
Yes, exactly. The slides, we won't talk about where they're hosted. Sorry, there was a question?
You should try something like Internet Explorer or
Yeah.
or Microsoft Edge.
Oh, I
Do
don't
that
think they're
quickly.
using a JIT. Just still parse
Can you put up the command again, just so you can test it, just to see if it.
Parallel is awesome. For the CyberGrant challenge, the first iteration of our cyber reasoning system ran on parallel. The whole thing was just these like hacky shell scripts run using parallel pipes to other things that run parallel with random timeouts. It was insane.
Yeah, so when you parallel, when you pipe out of it,
Yeah. So parallel
sets
will
all
join
these
them.
processes up and then
Yeah. Maps them out, joins them together. It's very nice. Very nice.
Why does it have to not like you?
You're trying this in Windows? In
Like,
Sigma or something?
you also see how it works on Edge. Yeah, I want to see if it works on
All right,
Edge.
we'll move on, but it's a good thing to explore. Where are my slides? Okay. So if you have a JIT that is not safe in that way, you of course find where the shellcode page is. This might require other memory corruption exploits or memory disclosure exploits. For example, abusing a null terminated, a lack of null termination on a string. And then you now know where to write. You write your shellcode there using another memory corruption exploit, and you redirect execution there using another memory corruption exploit. And now you're running shellcode. All right. So that's for safe, unsafe JITs. For JITs that are more careful, let's say you have a JIT that protects. What can you do? An interesting thing about JITs is that it compiles JavaScript or whatever code that generally, very frequently, for example, in the browser case, you control. You can create a page that has whatever JavaScript you want, right? And it'll execute in the sandbox, in the JIT. And the idea, of course, is that there are no memory corruption bugs. There's no way to take control, and you can trust Google.com to run stuff on your computer. But in the presence of memory corruption, this quickly becomes a liability. So if you create code with certain constants in it, so a string that has some binary data, and that gets just-in-time compiled, that string will end up getting placed in your JITted code. Strings you can specially handle. You can say there's no reason for strings to be executable, they'll put them in a different page. You can do the same with numbers. Right now you can't handle them as well. So you basically have these constants that end up being just-in-time compiled, written into the executable page, written to the writable page, and then the writable page makes them executable and no longer writable, and then you can corrupt another code pointer, assuming you have another vulnerability, and you can redirect the control flow into the JITted code, into that literal. And suddenly you have managed to inject shellcode without actually explicitly injecting shellcode using any sort of vulnerability. All of that happens by default. The only vulnerability you need is to redirect execution into that part of the page. Cool? Any questions on that? All right, this is called, usually actually, an interesting thing is that you can have 1 billion of these evil strings, or however much, right? And you can dynamically create them, in fact. You can just have a loop that creates new variables with new code constants inside them. If you run that loop a lot, the browser will eventually decide to just-in-time compile it, push all that out. You have a ton of this code of your shell code, then you might even be able to carry out the attack without knowing the entire location of the just-in-time compiled data. Who here remembers which one was it? The position-dependent executable, where you had a probabilistic attack that worked 1/16 of the time. Right. Imagine if you had an attack that worked not 1/16, but much rarer, right? 1 out of 400,000 times. You could still, of course, run that, or you could spew, if the situation allows, tons and tons of copies of your shellcode, so that there was more addresses that were valid that you could hit and then start executing from.
So are you saying that instead of keeping the string out in some other memory, they just put it into the memory where the code is, and they still treat it as data, but because it's in the same memory as code, it's now executable?
Correct. Yes. Strings, honestly, I put the string because it's an easier example, but you could conceptually think it's very simple to make this not work. You always put strings in some other location, and you could do that.
Is there a, is it ever done, like, they run the program, process, and then they run something else just to push out of cache the page that string is loaded on, but not push out of cache the page that loads that string, and then repeat multiple times so that every time it's a cache miss, so that the JIT says, oh, really, this is a big hit.
So the question is, can we force, if I understand your code, can we force the JIT to put, even a JIT that tried not to put the string into the executable page, can we force it to put in the executable page by messing with cache such that the only way this could run fast is if it was in the same page? Is that correct? Probably, I'm not sure if the JIT has that level of intelligence. Yeah. But you don't need to, right? So realistically, I put a string here because it's easy. You could imagine, you could say var evil equals 0x 90, 90, 90, 90, 90, 90. That is an integer constant. That will end up in the assembly. And that makes sense to put in the code. See math and the
Were you suggesting filling up a lot of memory with knobs? So you have a knob sled.
Exactly.
Jump right in here.
Yes. And so we haven't gone into knob sled, but hex 90 in x86 is a no operation. It's an instruction that does nothing. So if you have a bunch of those instructions, that serves as a safety net. If you land anywhere in those instructions, you will start executing to the end of them, and then you can put whatever you actually want to execute afterwards. Yeah. Zach. Knopfsled. Okay, cool. Any questions on this method of bypassing a JIT?
Did you mention how you could move your component? Is it just like
That's situational. That requires a different vulnerability. So right now, this is really how do you get your shellcode to be executable? And then redirecting the pointer, that's a whole different game. That's more like, let's say you have a buffer overflow like you did in homework 4, right? And likely that'll be the situation in these homeworks. For the most part, the actual control redirection will be simple. It's getting shellcode that's accepted and that is executable. That'll be hard. I mean, in this homework. In the real world, they're both hard problems, right? But I'm not expecting you guys to start exploiting Chrome this week. Although that would be cool and very lucrative for everyone. All right. So we already discussed this, but essentially JIT is everywhere, right? These aren't theoretical problems that might occur. These are serious things that happen now. JIT spraying is a major area of research that people are trying to figure out how do we prevent this, right? Because even if you don't know about a memory corruption vulnerability that could redirect someone into your randomly into your JITted code, doesn't mean it doesn't exist. Cool. All right. So that roughly covers the modern case of where to inject. Unfortunately, of course, this isn't as prevalent as fortunately for the world, unfortunately for shellcoders, it's not as prevalent as it once was. Shellcoding definitely is losing some of its luster in terms of the importance, but it's still very fun. It's an awesome thing.
when are we gonna have a break?
Let's have a break now. So let's have a let's have a 15-minute break so I can go to the bathroom.
What's your
All right. Let's get the show back on the road. So we figured out where to inject. Let's pretend we now know. So the second question is, what do we inject, right? Any random set of bytes isn't going to be code. On x86 it actually would, most likely. But let's say normally no. So what do we want to inject? Of course, we want to inject some code that either gives us a shell, or in the case of this class, it opens the flag and sends it back to us, right? So let's say we're working under these two assumptions, or under these two situations. Situation 1, execing bin sh, who here knows what exec v does? Exec ve. Exec v is a system call. Exactly. Hold on. Zoom in. Exec v replaces the current process with whatever you provide. So it would basically execute /bin/sh. And we covered this in class 2, if I remember correctly. And what you give it when you call it is a file name and then pointers to an environment and a arguments, and you can just make those null, and it'll happily execute bin sh. Maybe a pointer to null. The other option is you can read the flag. So you can open the /flag file and write it out. This is a cleaner option. You don't have to deal with problems like, for example, /bin/sh will drop privileges when it starts up, depending on what system you're running on. And so then you need to use /bin/ anyone remember? KSH or something else, exactly. Should be all sorts of flashbacks from homework 1 and 2. So that's one type of shellcode. You put in code that will call this. The other type is, you put in code that will open the flag file and write it. Has anyone ever used send file, the system call here? Yeah, so send file is very cool. In one system call, it'll read and write data. You give it an output file descriptor. You can see we gave it, what's going on?
Was it one of the challenges for writing?
Yes, exactly. Yeah. So this is how the win function was implemented. You give it an output file descriptor, an input file descriptor, the offset where to start reading, and the number of bytes, or to start transferring, the number of bytes to transfer. It'll transfer data from the input to the output. Super nice. Or you can do the typical open the file, read the data somewhere, write the data somewhere. What might be the advantage of send file over open, read, write?
I didn't notice until I saw the man page, but it doesn't transfer the data to user space. It happens within the kernel, so it's faster.
It's faster. From a hacking perspective, why is that good?
Stays at elevated privilege.
Why is that good? Or, sorry. I guess that's equivalent to saying it stays in kernel space, but why do we care if the data stays in kernel space? It's uninterruptible. That was what Zach just said. That's also a good point. Once you trigger send file, it'll likely work, but why? It's very rare that your shellcode will get interrupted. It's very small.
Why is it good for hackers?
For hackers.
Like you said, in case it gets interrupted, at least it's fast, so it'll do the shit fast.
We can change file descriptors.
We can what?
Can we change file descriptors
Using send file?
before we launch the program?
We can. We can change, like file descriptor 1 points to something else, but write will do the same thing as send file in that scenario.
Does it avoid buffers?
Yeah. It avoids buffers. If you do the following shellcode, the standard shellcode, open, read, write, you do it like this. You open /flag null, you read from whatever file descriptor into some buffer, however many bytes, and then you write into standard out from that buffer, however many bytes, right? What do you need for that? You need a buff, a writable location. And it's not always very obvious where a writable location might be. There might be no writable location. You might be screwed. With send file, the kernel, somewhere in the kernel is that writable location. So that's exactly right. We use send file in this case because we don't need a buffer to write stuff, to read stuff into. Cool. All right. One thing that we do need is the string /bin/sh or /flag. As we'll see what we pass to, let's just create a create an open read write shellcode. Getting a little bit ahead, but we're going to write it in assembly. All right. Hold on, I need to look ahead. That Intel syntax. Anyone have any idea why we do that Intel syntax? Because AT&T is wrong objectively, not because I hate them. Because it's wrong.
It's use NASM assembler.
You can use yes.
Save yourself a line.
You can use the NASM assembler, but then what do you do if you're trying to assemble PPC shellcode or bits? So we're in x86 land, so we're gonna write some quick shellcode in assembly to do open read write. So let's get a. We first have to do open, then we have to do read, and then we have to do write. All right. So let's see what openreadwrite.c would look like. This is what we want to do. Open/flag, and if we do man open, man to open, this is the system call documentation, is section 2 of man pages. Here we have, this is how open works. We give it a path name and a flags. What are the flags? These are the flags, the creation flags. You can open a file in different ways. You can open it in append mode. You can open it in write mode. You can open it in read-only mode. I'm going to tell you, to save you a lot of pain, that null is read-only mode. Okay? Cool. Okay. So, we open the file. Now we want to read the file. So we need a buffer somewhere. So now we do a read from the file descriptor, and of course, do man read. Here's the read. File descriptor, the buffer, and some large number. And then we do a write into 1. What's 1? Standard output. Our buffer, 1000. And that's it. So let's compile that. Sorry, C doesn't have this null by default. 0. Read-only mode is 0. And we execute open read write. And why do we have a bunch of garbage here?
That's the uninitialized buffer.
The uninitialized part of the buffer. So if we read in, we try to read 1,000 bytes, and then we try to write 1,000 bytes. The file doesn't have 1,000 bytes in it. The file is very small. The file has 36 bytes in it, right? So we have a buffer that has a bunch of garbage. Do you remember uninitialized memory problems from last class? We have a buffer that has a bunch of garbage in it. We read in 36 bytes into that buffer. So the first 36 bytes of garbage are overwritten with our flag. And then we write out 1,000, which also writes out garbage. In this case, we got the flag. We don't care. All right. So that's open read write. Let's look at what this looks like on the assembly level. And let's close this window. All right, so here's our main. Nice and simple. Oh, what's wrong with this picture? It's not readable. Much better, right? So, main is nice and simple. We push RBP, blah, 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 blah. We've seen this a million times. What do? We do stuff we call open. We do some stuff we call read. And we do some stuff and we call write. Cool? Cool. What are some problems with this? If we treat this as our shellcode, and we take this shellcode, and we inject it into another process, verbatim, byte by byte, and we redirect execution to it.
Is the buffer not there?
That's one problem, is the buffer won't be there.
The length,
The what?
the length of the shellcode.
It's pretty long, but you know, in your the early levels, you get like 4 kilobytes to inject, so it doesn't matter.
The string.
The string is a problem, so the string is, but the string is not as much a problem as you might expect. So the string is passed to open, right? That's /flag. You can see it being accessed here. It's the first argument, RDI, and it's accessed RIP plus F4, so it would be at whatever this plus F4, so you could just send that along all those bytes, including the string, and it'd be happy.
The zeros, the null bytes.
Null bytes, so we'll cover this later, but sometimes the way that you inject your shellcode gives you enforced constraints on what values the shellcode can have, but that's not it. What else?
Are the syscalls not in the same spot?
This doesn't use syscalls, and that's the problem. So what this guy does is it calls libc wrappers for system calls, and these libc wrappers live inside this the memory space of this program, and so it'll call 610, which is 610 bytes ahead of the next instruction. That goes into, so if you look at, here is 765. If you look at where open at PLT is, oh, I see, never mind. So it's 610, wherever it's located, and here's open at PLT. Open at PLT, this is the PLT stub that resolves using the linker, gets the address for the open function in libc, and jumps there, right? This is, we went over this kind of life cycle in class 2. What is the problem with that?
The address can vary. Depending on the size.
The address of what?
PLT.
In essentially, yes, exactly. If you just inject this shellcode, right? Just this code as your shellcode and start executing it. When it calls this, that is the address of open relative to this program, but it almost certainly won't be the address of open relative to whatever program you're exploiting. Problem number 1. Problem number 2, you might not even know where the program you're exploiting is located in memory. You might only know where a readable or a writable buffer is located in memory. Or you might not even know where your shellcode is located in memory, as you'll find in this assignment. So it might be very tough to call the open function in the program, even if you send in not just main, but that entire binary as your shellcode. In order for this process to work, this process right here, the program needs to be properly initialized, and it's probably initialized by the loader, which knows where everything is and can write the correct addresses to various places, and you cannot. because you're not the loader. You're a hacker that has managed to inject some shellcode. So you don't want to use these libc wrapper functions. And in the end, all that these libc wrapper functions do is actually execute the system call. So let's step through open read write in GDB. All right. So here we are, moving RSP, blah, blah, and we're just going to step through open so I can show you what it does. Right? So we're stepping, right? We're setting everything up. Here we're about to load our address into RDI. So we step one more time. And right, I have this weird situation. And here we see RDI is pointing to flag, and everything's happy. And we're about to jump to open with these arguments, with file, with the file being a pointer to our flag, with and so forth. Right, everything is happy. So we call into open. So now we are at the PLT stub of open, right? The memory, the library resolution part, and we jump one more time, and now we're in open in libc, right? And we continue executing, and this does some sanity checks. We don't care about that because we're not going to execute this function then anyways. I just want to show you that eventually, after a long time, it will set up and execute a system call. So it'll move a bunch of stuff into a bunch of registers and then call syscall. Boom. Syscall is an instruction. I'm sorry?
That's inside libc.
This is inside libc. Syscall is an instruction that on x86-64 triggers a system call. That's what you really want to do when you call open. That's what libc eventually does. It's the only way to open a file in 64-bit x86. There's in kind of 32-bit x86 you use a different instruction, int 80, which triggers an interrupt. It's not important, but basically there are instructions in different architectures that will trigger a system call, right? And actually, I take it back. This isn't the only way to trigger a system call, but let's pretend it is for now. So there's a syscall instruction. Syscall instruction runs, and now if I hit enter after the syscall instruction, we will have our open file, right? So if we look at right now our open read write, and we do look at the open files of open read write, the program, just standard in, standard out, standard error. We step one more instruction after the syscall, it opened the file. Syscall is what actually opens the file. The library function is irrelevant. The library function injects all of this other crap that we need to know the address of libc, or we need to know the address of the stubs inside the binary itself. So we don't want to write shellcode that relies on libc wrapper functions. Right? You can just write the syscalls directly. So, how do we make GCC output syscalls directly? Don't do it. It's a giant headache. You're wrangling GCC. You have better things to do with your life. Just write the shellcode in assembly. You will need to write shellcode in assembly anyways. You might even need to write shellcode by hand with the different bits, but probably not. So, how do we write this in assembly? It's very simple, actually. So if you scroll up here, what syscall did when we ran it. Basically, we ran syscall with an argument in EAX of 0x101. That is the system call number. And it actually ran, this is libc obscuring stuff for OS. It actually ran a different system call, openat. We don't want openat. We just want it open. Right, so what does openat do? Let's look. In the man page, because whenever we want information, we go to the man page. Openat. Actually, why didn't I just man openat? Anyways, openat has a man page. It's along with open. So open takes a path and a flag. Openat takes a file descriptor, a path, and a flag. So you can open relative to a directory. So it's being nice and smart and give, I guess, opening something relative to whatever, where we are right now. Can it? I don't know. But we can look at the description of it. Openat operates exactly the same as open, except for the difference described here. If the path name is relative, it's interpreted relative to the directory referred to by the file descriptor. And you can have a special value basically at the current working directory. Anyways, we don't want openat. Openat is some, I don't know, more stuff to set up, more arguments. You want shellcode to be as simple as possible. We want open. So, and we also don't want the wrapper function. We want to do it directly. So what do we want to do? We want to do something, 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 and eventually we call the system call, right? And one of these somethings, and I'll tell you this as a free hint, one of these somethings sets the, because system call is kind of a general purpose instruction, it doesn't know which system call you're trying to call. So one of these somethings is the system call number, and 101 is openat's number. So how do you know which number is what system call? You Google for Linux system call number x86-64, and I can tell you that one of the top results will be a chap named Ryan A. Chapman, who is a hero because he wrote this little table that you can also, of course, recreate yourself by parsing the kernel sources for different numbers. But Ryan A. Chapman made a real name for himself by publishing this, and every single hacker that does binary exploitation is very familiar with the name Ryan A. Chapman. So we can figure out what open is by looking, oh look, here's open and it's number 2. We can look at openat, of course, and it's not. Oh yeah, it's 257, which is hex 101. Exactly. All right, so this is decimal. Open is 2. Cool. So now we have one more. Where's my, there. Now we have one more part of the puzzle. 2. All right, now we want to set up arguments to open. So one of those arguments, the second argument is 0. Do you agree? Or do you remember why? Because when we created openReadWrite.c, that's the read-only argument. We just want to read it. We don't care. So let's move. What's the register that has the second argument? RSI. RSI 0. All right. So what is left? One thing is left, and that is the string, right? So there are 2 ways of setting the string. And let's put Ryan Chapman to the background for a second. One is we can add the string after our shellcode and do either an instruction pointer relative reference to it, or do a trick to get its address. We won't go into the trick really because it's obsolete.
Is it obsolete?
The call pop.
Yeah.
Well, now you have rip relative addressing.
English only, please.
Okay, let's go into the trick. So, how do you add the address of a string? So you have a string, and the string is bin slash flag, right? You want to open slash flag. Okay. And honestly, it's been long enough that I don't remember the syntax. This is not it. This is NASM.
Are you trying to do something like dot ASCII?
Yes. Yes. Thank you. Yes. Okay. So you have a string somewhere, and now you want to get its address. Like I said, you might not know where the shellcode is. Right? It might be placed in a random. It loaded into some random address. Depends on your method of exploitation. So if you can create a new label. If you what? Yes. Yes. That's basically what we're doing. So what you can do is you can do call shellcode. And here you have your label for your shellcode. And here you do pop RDI. Why does this work? What happens here?
Call pushes RIP onto the stack, so when you pop it, you now have the address that was the previous instruction pointer, which pointed to slash flag.
Exactly. So what happens is this. Call runs, or call is execute the call instruction. What it does is it pushes the address that you will return to onto the stack. You've all overwritten this address. You're very familiar with it, right? Call ret. And then, instead of returning to the address, we just pop it into a register, right? And that is the address of this flag, because that is of our string, because that's the thing that's right after call. All right? So let's actually assemble this, emulate it, and watch what happens in real life. How do we assemble it? There are two ways. This is a shellcode fully formed that we'll look at later. You can write your assembly in a hacker assembler like NASM and get it to output the binary directly. But then you're using kind of hacker-specific tool chains. Hacker-specific tool chains are usually maintained by a hacker, and they tend to add things as they need them. So NASM is an assembler for x86 and AMD64, but it won't assemble for, I think, for MIPS and so on. Whereas if you use the standard GCC toolchain, you do have this support. So if you're going to use the standard GCC toolchain, and it's a little bit of a pain in the butt, but we'll make it through. So you can assemble using AS. It's the GNU assembler. You give it the shellcode and the output, and it makes it into an ELF. So we do open. Actually, let's open read write ORW shellcode to differentiate it from this guy. So we do, since that is logged. Okay, we do this. We do AS ORW shellcode, and we give it an output of ORW shellcode.o, and this probably won't work because we probably screwed up something, but it worked. All right. Don't party just yet. So, ORW shellcode.o, we can dump it.
You typed in Perl. That's why it looks wrong.
Thank you.
That's not why it looks wrong, it's why it is wrong.
Exactly. So, here we have our disassembled stuff. So first we do this call. It does call B. What is B? B is the address of shellcode, or the offset. And in reality, you can see this call isn't B, it's call. This is call 6, which is 6 bytes ahead of this, of 5, which is B11, right? Because it's relative to the next byte, and
Say that.
Okay.
That's been SH that is
Yes.
trying to read as an instruction.
Or slash flag. This is slash F L A G. Okay? And here is where we start up again. Pop RDI, move syscall. Cool? So let's we can actually make this into a binary and actually run it. If we do LD, we do oro shellcode.o, oro shellcode.elf. We do have a start, but it's not global. Hold on, let me make start global. Shellcode.s. Here's our start. Now we can actually compile it. You don't need it if you're not going to be doing this, but why not? So we compile, boom. We assemble, boom. And now we can execute. And it, of course, still sec faults, probably because it keeps executing garbage after that syscall, but that's fine. We can strace it. And here we see our open flag. Cool, huh? So now let's GDB it step by step. Break start. Run. So here we are. We call the shellcode. Our stack right now has a bunch of shit on it. Here is our argc. This is a pointer to argv. So this is the argv pointer, points to this, which points to this string. This is the sec argv1, which is null, the terminator of argv, and then here are our environment variables. Pretty cool, huh? This is our bare bones elf. Very exciting. So now we step. Now we just called, and on the stack, yeah, so it didn't update this yet. So RSP is now pointing to here. I'll one of these days I'll actually get to the bottom of why my Pwn debug is a piece of shit. But if you look at what is at RSP, it is the address that I claim is where our string is. Cool? And now, excuse me, we're about to pop this. Boom. So now RDI, oops, points to our string.
Okay. So I don't know assembly that much. Why is flag there? I honestly have no idea.
Because
Your assembly code did, 'cause I feel like you're supposed to save a string into a variable name, and you save it into
so of course that is what would happen if you wrote this in C and compiled it. The compiler would put your strings into a variable somewhere in the read-only data globally or whatever, right? And then it would reference to it and so on.
Okay.
But that's the compiler doing that. When you write assembly directly, you have ultimate control. Or you can have ultimate control. And here, literally what I told the assembler is put in a call instruction. And then put in the letter /, the letter F, the letter L, the letter A, the letter G, and a null byte. Sorry? No, this is direct. This is not an integer, it's just a set of strings.
Right.
Yeah,
So
so like-
it puts the bytes.
Yeah, just directly. Like literally, I said, I don't care what you think is right, assembler. I want you to put in random text in the middle of my code. And it just does it, right? Because this is assembly. Because no one's supposed to write this shit by hand in 2018, but we do now. So, it literally emits a call instruction, and then it emits ASCII. If that was anything but call, of course, if it didn't jump over ASCII, over the /, it would continue happily executing the /, the F, and as we saw, / was valid, but then afterwards there's bad instructions.
But it'll only work for something that's 8 bytes or less.
No, I can do anything here. I can do supercalifragilistic XP All right, boom. So we're gonna assemble it. AS. We're gonna link it, and we're gonna run it. And of course, with S-trace, and it happily puts supercalifragilisticexpialidocious. Because if we obj dump it, it literally puts in all of these bytes. You can see all these bytes look very printable. OX6 whatever is obviously a lowercase. 7 whatever, the low 70s are lowercase too, and so on. It happily does it, right? So what I told it is, make a shell call, put in all of this, figure out where this next instruction is, and have the call point to that, right? Very handy. Without RIP relative addressing, this is the only way to get the address of the flags. That's no longer the case. So this was something you had to do on 32-bit x86. Those dark days are behind us. If you are working with 32-bit x86 shellcode, most likely you are solving a lame CTF challenge. Of course, there is still real code that's 32-bit x86, but it's less and less and less and less, right? Unless you're a very specialized hacker. In the real world, you're not likely to run into it.
So for this homework, are we going to be writing assembly code?
You better believe it. You're writing shellcode. You're going to write shellcode. You're going to write shellcode that is position independent. Almost all shellcode is position independent nowadays. Now you're going to write shellcode that doesn't have null bytes. You're going to write shellcode that is sorted. You're going to write shellcode that is statistically analyzed for certain properties. I mean, you're going to write a lot of shellcode. It's going to be awesome.
We missed the drop deadline.
You're stuck.
And this is a 1-week homework?
Yeah.
We have a long way too long. Plus 20% flat. Would it be like entry level?
Yeah. So the shellcode that I have on the slides and that you're writing right now will work for like the first 3 levels probably, right? Like, don't panic. Don't panic. Yeah, panic is the first step, but panic a little bit.
Begin panicking now then.
All right, anyways. So, we are no longer living under the confines of x86 32-bit. All modern systems that are relevant, let's say AMD 64 and ARM, have position RIP relative, so instruction pointer relative memory accesses. So, what we can do now, and obviously it doesn't really matter, but it's just it looks a little different in assembly. We say, here's our string, and here we can do load effective address, RDI string. I believe that'll work. So let's find out. No. Oops. Why did I do that? This should be good. Okay. Now we can strace LD and strace. Let's make sure that we are actually. Oh yeah, if it all worked, it should be fine. Okay, LD, strace. Yeah, and we have so now let's look at what it looks like. So nice and simple. Why is there a 0 here? Oh, I see, because this is a long instruction. So instead of call, jump over the string, pop, we now have a nice and simple load the effective address of. Ooh, that's bad news. Why? That's not very nice of it. Let's GDB it to single step. This is problematic.
Wait, no, try XS.
Try what?
XS. X/S.
Oh, what? Of this?
Yeah.
Yeah, it is the flag. But would this work if we loaded somewhere else? Is GDB trying to simplify something for us here? Or is it...
Is there any chance that GCC's assembler decided to simplify it for you?
Yeah, that's very possible.
The problem we talked about is that that's a hard-coded address instead of RIP plus.
Yes, exactly. So this should be RIP plus something, but it's not. It's a hard-coded address. That's very not nice. What if we do this? Will it get... Oh, hold on. If we assemble it... Can we tell it to do position? All right. So this is where things go off script. Nope. I'm sorry?
Try F-pick.
I didn't like it.
Can you encode it yourself? Just rip plus.
I can, but then this requires knowing how many bytes this is, but that's fine. This is 5,
How about that online
6.
assembler? It's a really good one.
Yeah, there's a number of things you can do. You can use an online assembler. You can Google for GCC AS RIP relative address. There we go. Oh God. There, maybe?
Why is it?
No.
Like wrong?
Oh, there you go.
So it's message RIP. Let's see. It's assembled. Hurrah! Google for the rescue. All right, to the rescue. For the win. Okay, so now we have a RIP relative addressing thing that loads the flag and everything is happy. Let's run LD.
What was it again? What did you do? Can you grab the...
Here's the shellcode. Here it is.
So you
Very
loaded
cool.
the string into the RIP registry?
So this is a
That's a weird...
it's a weird, so if I did this, if I did this, this would be load the effective address of whatever value is stored in RAX plus 10, right? If I did this, actually I don't know if that worked. If I did this, it would say RAX, I don't know if that would work, but this basically says whatever value is currently in the instruction pointer, which it knows, because it'll know where, either if you don't have, because it can produce RIP relative addressing, and then it'll add this offset, the offset from the next instruction to string, which is 10. So this is the offset from, I can see it's not very intuitive, because you see this as an absolute address. Right.
So basically you're adding 10 to RIP, and then RIP is now located where that flag is.
You're not adding 10 to RIP. You are reading that.
Adding whatever the string is. Now,
You are taking the value of RIP, adding 10 to it, and storing it in RDI. Now RDI, the first argument of our system call, is pointing to the flag.
okay.
It's dereferencing it to the load effective address. So the load effective address, it doesn't do the dereference. It gets the address that it would dereference.
Is it 10 because the instruction pointer at that time? Would that
Yeah.
depend on the responder?
Yes. If I've added more instruction between those two, it'll be more than 10. Yeah. Other questions? Cool. All right. So now we have a modern position-independent way of doing our open read write. This is one way. Honestly, this is a great way. So let's just AS, LD, strace, Boom, it opens the flag correctly. We can GDB it. Break at start. Run it. Here we are. Load effective address, RDI, blah, blah, blah. And you can see it plus OX10. We're at 7.8. The next instruction is at 7F because this instruction is whatever, however many bytes. And it will load the value 8F into RDI. Step XS RDI. Pointing at our string. Cool? Cool. No jumping over anything. The disassembly makes sense. Much easier. The other thing you can do, and there are situations where it's better, situations where it's worse, and what I actually have in this example shellcode is you can see I actually push the value of /flag 0000 onto the stack, and I move the stack pointer into RDI. Cool? How does this work? Let's write it. So this is way number 3. Let's comment that out. Way number 3 is, we move this away. We do push, move RAX. What is the value of /flag? Okay, so let's look at man ASCII. / is 2F, right? So let's say 2F. What's next? The L. Whoops, that's the lowercase. Oh, sorry, the F. Lowercase f is 6. Lowercase l 6c. Lowercase a 6.1. Lowercase. Thank you. Lowercase g 6.7, and then a bunch of zeros. Right. So let's see. F L A G. What's that? 00. All right, you guys caught it. Endianness is critical here. What this will, if we do this, and then we do push RAX to write our flag onto the stack, we're going to end up opening gal / or not even, because it starts with zeros. It will be a blank string. So instead, let's keep that as reference. So what we want to do is 000000 67 61 6C 66 2F. All right, and then we push that. So now it's on our stack pointer points to the string flag, and now we move RAX. We move into RDI. Load effective. Move to RDI. RSP. Does that make sense? So let's assemble it. Quit that. Okay. Assemble it. Boom. Undefined reference to string. What? Assemble it. Where did you get the reference to string? There's nothing weird going on, right? It's not silently failing. Is it somehow... What the fuck? But that's a comment. All right, anyways. Accept the mystery and move on. All right, so object dump it. Here's our thing. It moves this absolute value into RAX. Then it pushes RAX. And then so on. So let's GDB. First, let's strace it. Open the flag. Let's GDB it. Break start. All right. So moves into RAX. Boom. So now if we look at PX RAX, here it is. So if we step, it'll push it. So now let's look at RSP /flag. If we step, it'll move RSP into RDI, and now RDI. and RSP, of course, point to our flag. So that's a third way of getting the string. Covered 3 ways. 1, jump over it, pop the return address. 2, rip relative addressing. 3, build it and write it to the stack. And they're all useful situationally. What is the advantage of the rip relative addressing over this one?
The code is position independent.
It's position independent in both ways. So here, no matter where the code is, yeah, you're not relying on anything inside the code. All 3 ways that we looked at were position dependent, in fact. Why is this? What is the major difference? My claim is the rip relative version is better. Why is it better than this? So if you're in 32-bit land, for sure /flag won't fit, but you could do 2 different pushes instead.
This one modifies the stack.
This one modifies the stack. That is not good when you have completely screwed things to the point where your stack is not writable anymore. And this can happen for a number of reasons. 1, whatever you did to get into shellcode, clobbered RSP, happens a surprising amount. Or 2, whatever you did to remap your shellcode as executable, clobbered RSP. Or if your shellcode is on the stack, you remapped it as executable, not writable, and then jump to your shellcode, you're now on a non-writable stack. I mean, I've seen, like the Blade Runner person, I've seen things you wouldn't believe. But there are things that unmap the stack by accident. There's a lot of bizarre situations. The nice thing is, if you are in this land, you don't care, right? The not so nice thing is that has a null byte at the end. Sometimes you care very much about that. So normally, if you cannot have null bytes in your shellcode, a variation of this to get rid of these null bytes is necessary. How might you get rid of null bytes in that constant? That's but you could add a bunch of two Fs, but you need the null byte at the end still.
Make a register 0 and then push it.
But then yes, you could do that. So you could basically have, instead of these 3 bytes, you have 2F, 2F, 2F. So it'll open // flag. Of course, that still works, right? And then you push RAX, you XOR RAX, RAX, and you push RAX again. No null bytes here. Another way, it's a little tricky because you'll still, even if you do, oh yes, I see what you're saying. So you can do 1 1 1 1 1 1, and then you could do shift right RAX by 24 bits, and you want a logical right shift. Oh no, you don't. We won't go into the difference between logical and arithmetic right shifts, but you shift that to the right, also works. You see why? Shifts out all the ones, leaves you with a nice /flag. Final one I'll leave you. Oh, does this work?
No.
No, why?
I think RAX has a null byte.
RAX, this one?
Yeah.
Here?
No, I think to define the register RAX, you have to put a null byte.
It depends on what instruction. So but I agree with you that this will have a null byte in it. Why will this have a null byte in it?
24.
Yeah, the 24, in reality, this operation, actually, let's check.
You could exchange, you could XOR like AL or something with itself.
I lied. It doesn't have a null byte. I lied. This is a single byte argument. But usually, whenever you have a constant, you have to be very careful. because if that constant is, when you write it, you write 1. But if that's a 5-byte or a 4-byte number or something, that instruction takes, it'll do 0, 0, 0, 0, 0, 0, 0, 1, and you've just stuffed your shellcode full of null bytes. And actually, I realized we don't have the context of why this is a problem. We'll get into that in a second. Let's just run that, and I'll show you that it works. It works. Let's GDB it. All right, here we have our shellcode. So obviously, RAX does not point to valid memory right now, but once we rotate it, RAX is the string here. And then if we push it, you can see that it pushed the right stuff. So this has the advantage that it's nicer in that sense. It is in the sense that we control better what bytes are in here. Another thing we could do, of course, if it's not the shift, we could XOR, essentially write this XORed with some whatever, for example, OX 01, 01, 01, 01, 01, 01, XOR this, right? So this, the assembler will calculate the value of this constant and write that in. It'll have no null bytes because all of these will be turned into 0, 1. And then this will be clobbered it'll be XOR 0, 1, 0, 1. And we could also do this. And so on, right? And now we've encoded and then decoded our shellcode, no null bytes. There are a lot of different things you can do. But let's go back to our happy place. One thing to get around this whole null byte problem, the null byte here to terminate /flag has to be at the end of /flag. In this case, that's the last byte you write. Very frequently, there's already a null byte there, right? Whatever memory you're writing into. Frequently, it's either usually going to be a null byte or a new line. New line's worse. Null byte is not as bad. Even if there's a new line, you can, in your shellcode, find it and write something to it. But then it requires it to be writable, right? All right. Anyways, moving on. We've opened the file after half an hour to 45 minutes of shellcoding. Cool? Now, what's next? Read. And now we're very quickly going to run into this problem of where can we read to? So where's a readable buffer? I'm sorry? We can send file to avoid the problem, but for now, we can use the stack, right? So, read will end up as a syscall. What is the syscall number of read? Is it 1? So how do we find this? Syscall, Linux, Ryan Chapman, our good friend. Word of warning, Ryan Chapman only knows x86 64, MD64. If you're shellcoding for MIPS, PPC, ARM, some of which you might need to do, you will not be able to rely on Ryan A. Chapman. All right, read a 0 is the bottom line. And you should memorize that. Obviously, trying to figure out how to get around this null byte. It's not that hard. You can XOR RAX instead of move RAX 0. This instruction has no null bytes. This instruction has null bytes because of this constant. All right. Move RAX 0. Then what? Then we, what do we do? We need to set 3 arguments. Do you remember the arguments? The buffer is which argument? The second argument, which register? RSI. So we can use the stack. Right? We don't care anymore about what came before. We've already opened the file. /flag is irrelevant, and it wasn't on our stack anyways, right? So what does this imply? What does it require?
A writable stack.
A writable stack. So now we're back into writable stack territory. All right. What else does read take? the size. In what argument? Third argument. So, which register? RDX. What size do we want? Enough. And the file descriptor. What argument? Right. So the file descriptor is returned by open in RAX, which is the return value. And it's passed as the first argument to the syscall. And so we need to use RAX before we override it with 0. Also, quite frankly, it's not that necessary usually to use the file descriptor as it's returned from open, because usually it's file descriptor 3 or 8 or 10 or 15. But programs, even real world software, typically has a set amount of resources open when you go to exploit it. So we can do this.
Why is it not important to use the file?
It isn't. Well, you need to pass the right file descriptor. But every time I run this program, this file descriptor is going to be 3. Yeah. In the general case, if the program opens some other files beforehand, it might be 4, 6, whatever. But you'll usually know from offline analysis what that file descriptor is going to be. Not always. So this is a good practice. Save the file descriptor. It doesn't cost us anything. In fact, it's better because this instruction has no null bytes. So we now have set up and called read. So let's actually do it. AS, LD, strace, read. So we read 3, we read this string, and we tried to read 1,000 things. We only got 36. Cool? So we read our thing. What do we do next? Write. So we can do syscall. What's the number for write? 1. Ryan A. Chapman or memory. So 0, 1, 2, read, write, open. It's not always like that. I think open is 0 on x86. I don't know. Anyways, obviously different, or not obviously, but one thing to keep in mind is different architectures have different syscall numbers, even in the same OS. In fact, if you're shellcoding for Windows, Windows changes its system calls on a patch level. Like every time Windows is patched, the system calls can change. They don't guarantee a constant interface, which is a pain. All right, so move into that. What else do we need to do for write? The pass arguments. So there are 3 arguments to write. 1, 2, 3. What's the argument? The first argument. The first argument to write. The file descriptor. Standard out. What's the problem with this instruction that's highlighted? Move RDI 1. Null bytes. How do we make an move RDI 1 that wouldn't have null bytes? There's a number of ways. We can do XOR RDI RDI. And you can, of course, disassemble stuff and verify that it has or doesn't have null bytes. This doesn't have null bytes. It sets it to 0. We can inc RDI. This doesn't have a null byte. It increments it. Cool. All right. Move RDI 1. RSI, second argument to read, is what? Our buffer, or sorry, to write. RSP, which is where we read the flag into. We will now write it out. And the third argument, size. How long do we want to write? Enough. All right. Assemble, link, strace, boom. Open, read, write. If we just execute it, it writes the flag and a bunch of garbage. And then it crashes at illegal instruction because it just keeps executing. Cool. What if we were, let's say, environmentally friendly and we didn't want it to crash? Halt. So let's say there's an instruction called halt. Will this avoid it crashing? AS, LD, execute it. Segmentation fault. It still crashed. Why? Because halt is a privileged instruction, you can't call it from user space. But if you call it in the kernel, it'll shut down your machine. So that's not what we want anyways. What else can we do? What do you do in a C program if you want it to exit cleanly? You call exit. Turns out exit, according to Ryan A. Chapman, is a system call. And it takes one argument, which is the error code. We don't care about the error code. And what is the? It's 60. We don't care about the error code. Move RAX 60. Syscall. AS. I'm sorry? No, Ryan A. Chapman, this is in decimal. Just something you got to remember. Ryan A. Chapman's a funny guy. Anyways, here we do the read, write, exit. Or W strip. Now cleanly quits with exit code 1, which is what happened to be in RDI, which is because we wrote it here.
Just out of curiosity, why did strace give a question mark as the return code? Because it doesn't return?
I think so, yes. That's my guess. Exit never returns. But it does see that it's exited with 1, right? So if you wanted to exit really cleanly, move RDI 0, AS, LD, execute 0. Oh, percent $sign is the last result. Cool? Very cool. So that's open read write. What does our shellcode rely on? A writable stack. That's no good. I mean, it's fine in most cases, but sometimes it might not be good. So, let's do something else. Let's do send file. So now, instead of open read write, we're just going to do open send file and exit because we're nice. All right, so send file. Let's start over. Ryan A. Chapman says send file is 40. Okay? RAX 40. The man page. Now we start looking at the man page. Man send file. Man page says first is the output file descriptor. What is that? Standard out is 1. Next is the input file descriptor. What is that? It's an RAX. Or, in this case, you can safely assume it's going to be 3. But it's an RAX. All right. Now, offset is 0, correct? RDX. What is the fourth argument? Enough. But what register? RCX. Enough. All right. Assemble send file .o, ld send file.o, send file .elf. Let's just execute it first. That's not expected. Is RCX the wrong one? What is it?
Chapman's thing.
Chapman's thing. We scroll all the way up. Chapman to the rescue. R10. So actually, before we move on, I'm going to fix my slides. That's interesting. I thought I tested this. R10. Good thing we have Ryan S. Chapman. All right, so here we go. Okay, so we are now, I changed it on my slides, but not in real life. R10, AS, LD, strace, send file, it works. Boom. Why don't we have garbage here? send file writes however much is read. See, the problem with our open read write is we just ignored how much we actually read. We can fix that, actually. If we want our open read write to be nice and not give us garbage, we can change this from enough to RAX, which is the return value of read, which is how much we read. But either way, it's fine. So that is now a cool shellcode. That's actually smaller than open read write because we only had to set up 2 system calls. You can squeeze it down a little more even. Yeah, gets us the flag. So we've gone through how to test your shellcode. There are 2 ways. One way is we used LD. If you have this .global here, .global start, we can use LD. We use AS to create the .o. We use LD to turn that into an actual executable ELF, and we can execute the shellcode. That's great, but you might need to test it in other scenarios. For example, without a stack or something. If you want to test it in other scenarios, you can write a little tester program. So that tester program will map an executable page of memory, read in your shellcode into the page, and execute the page. You'll see that most of the challenges will do something like this to load your shellcode. And then, of course, you can just cat your shellcode to it. Now, your shellcode right now is not a shellcode. It is an actual ELF executable file. That's no good. So what we can do is we can actually extract, and you can see, for example, underscore start. Wait, starts at 0? Oh, sorry. If we do .elf, you can see underscore start starts at some random address that it chose. I mean, the normal start address that it chooses. It doesn't make position-dependent code here. If we want it, so what we want to do to make it a shellcode and not a program, we want to extract these bytes. So those are the bytes that we will send to the whatever program we will load shellcode into. So we're going to use this command, objdump, or objcopy, sorry, -- dump section. And then we say dump the text section, which is where our code is, to our open read write, or let's do send file shellcode. And we do send file shellcode.elf. And it extracts it. And here is our send file shellcode. This is the exact bytes that were here. So 48 AD 3D 500000, 48 AD 3D. What? Oh, wait. I obj-dumped the wrong one. This should be send file. Yeah. 41000. And you can see it here as well. Cool? Very cool.
Jan,
Yeah.
why do you bother doing the object copy? Can't you just cat the .o file the AS produces?
Let's see.
It doesn't object copy too well, but it looks like you're just undoing it too.
So this .o has an ELF header around it, right? So it starts with 7FELF. It has all of these ELF headers that we discussed on class 1 or 2, whereas this guy is just our shellcode. And you can see it starts with that first instruction, and it ends with flag null byte. Guys, I have to run to the bathroom. I'll be right back. Discuss amongst yourselves. Whoa. From here, there's a crazy echo. Awesome.
I still don't know how to access the class.
Yeah.
I mean, I have like, I can see
what I figured we could get all those bits into a file, and we have that file. Yeah, but we also have to add like padding. It's like if we can go over it. I don't want to start this on Monday. Okay, let's do it. Friday night also. Yeah, I don't have time.
Still amazing. 16 Oh, you got the Oh, fuck you.
I don't even own it.
Intern AI.
All right. So we've now created our first shellcode, and we're ready to run it. So let's grab one of our challenges from this next thing. Homework 6 Charles. What? Yeah, Child Dude is the generation framework. I renamed it now to Pwn Shop, but I didn't rename the directory. So our stuff is going to be baby shell. Here is baby shell. What? Baby shell 1. Teaching. All right. This is the walkthrough version. So it says, all right, we're reading OS 4000. That's a lot of bytes into some address that it mapped. And this uses roughly this code, right? Maps it, reads it, executes it. I'll give it ASDF. Huh? It says it failed to disassemble this shellcode. These are my bytes, ASDF. At this address, it's going to execute it. Of course, it failed to disassemble it, so it's an illegal instruction. I can give it AAA. Failed to disassemble the shellcode. That should be valid x86. Maybe it's not enough A's. Yeah, so just, oh, interesting. So the library failed to disassemble it. Anyways, if we cat our shellcode to it, boom, executing shellcode, boom. So it's going to help you and show you the disassembly of the shellcode. You can see the massive amount of null bytes here. And here's our shellcode. And this is familiar. This is what we wrote. Okay? And this is the solution to the first challenge already. And maybe because we did too good a job the first 2 or 3, but we'll see. Okay. So, that's how you test it. Honestly, challenge 1, the walkthrough is a great shellcode tester. It'll load your shellcode, it'll disassemble it for you and show it to you. It'll run it. It's great. Use it. Moving on. Some complications you might experience building shellcode. Null byte is an extraordinarily common one. Because shellcode sometimes is string copied into place, right? Or at some point a string copy occurs on your code. And a string copy will stop copying on the first null byte. So, you noticed our shellcode has a ton of null bytes in there. How do you get rid of them? Well, one way to do it is instead of doing move 0, because this 0 is this right here, instead of doing move 0, you can do XOR. Let me show you the difference. So here's our move. And now we can do send file .s. Instead of move RSI, XOR RSI. This XORs RSI with RSI, moves that into RSI. What's the result? 0. So let's compile it. Let's produce the thing. Let's opt copy. Okay. Actually, we can also opt copy it out of that O as well. It doesn't matter. They both have that text. Cat that through here. And you see this XOR psi does not have the null byte. Okay? And if you have all the room you need, you can get any amount of any value. So you do XOR psi and then you increment it until you've built the correct value. You can also use shift in a very clever way and so on. Cool. XOR in a clever way. You can use a number of things to encode any value you want in any way. Yeah. One very useful thing, by the way, you'll notice here we have a bunch of zeros. We did move REX 2. We can do XOR and then whatever. Or an easier thing, we can move AL 2. Exactly. First, we want to zero it out because this won't zero out the rest of the register, but this will write 2 into the least significant byte. Let's assemble it. Let's opt copy it out. And let's run it. And here, no null byte. You'll also notice that this is shorter. Yes, it's shorter because this move is 1, 2, 3, 4, 5, 6, 7 bytes. XOR and move into AL is 1, 2, 3, 4, 5 bytes. Size in shellcode, the smaller the better. Right? So you will run into that as well. Oftentimes, your shellcode can't have new lines and spaces because of the way it's read in. If you do scanf shellcode, scanf will stop reading at a space or a new line. But it won't stop reading at a null byte. Does this have any new lines or spaces? It does not appear to. So that's a smaller problem. Sometimes, and this one's a bitch, shellcode requires printable characters only. Right? So however it's read, it requires printable characters. That's tough. And a lot of other situations. So I think I actually listed out some other complications. Other common problems. Your shellcode, some asshole might sort it before executing it. That might be tricky. Your shellcode could be compressed before execution or uncompressed before execution. Yeah, or decompressed. Shellcode might be encrypted or decrypted. I mean, anything could happen, right? And does and will happen. So, how do you get around these issues? There's a number of ways. One is very frequently you can say, okay, this part of code is going to be garbage. Can't do anything about that. It's just going to be garbage, right? For whatever reason. For example, I might need some decoy bytes to distract the sorting algorithm. And you say, all right, that's fine. I'll just jump over them and use the bytes that I have full control over to do what I want, right? And that's when short instructions come in handy. Do something, jump over garbage. Do something, jump over garbage. And because you have very good control in the assembler, you can craft shellcode that is exactly correct like that. You should understand, given the constraints of the challenge, what shellcode you can inject. For this, or what instructions you can use. For this, a disassembler is very useful. One that you can program. So Capstone is a disassembler that you can program. I, in fact, use Capstone to give you this. You can use Capstone in C or in assembly. Of course, you can use it in assembly. You can use Capstone in C or even in Python to go through all of the possible bytes that you can use and understand what instructions are available to you. For example, if you can only use small instructions, you can try to understand of all 2-byte instructions which ones are useful. And oftentimes, under these constraints, you will have to chain multiple instructions to do what you want. XOR to clear something and a bunch of inc, rex to get it to the right value. You can use on multi-stage shellcode in several ways. One is you can have an unpacking shellcode that modifies itself. This will be necessary. So, if something restricts you to some small set of shellcode, and to get beyond that, you need to write an unpacker. You might need to do that. You can use a multi-stage shellcode. So we should do this before we leave. Basically, if your shellcode just calls read and reads more data into whatever is pointed to by the next register, basically this read 0 RIP enough, that's a very short shellcode. You can get that down really short, actually. And then after that, of course, it'll read more shellcode, and you send that extra shellcode. If you don't go over this, I might give you an example of this on the homework assignment, and we won't have time to go into it. So a good stage 1 shellcode, you want it extremely short. So then you have the most, you can get around a lot of requirements that way. Problem with this, what if standard input has been closed? What if you can't read anymore? What do you do then? So once your shellcode is ready, injected in the real world, this can be very tricky depending on the vulnerability. In these challenges, it's not going to be very tricky. It's going to be very easy. These challenges are about writing the shellcode. Injecting it is going to be straightforward. And then you have to interpret the results. So we've been interpreting results all class. Boom, this is the result. We've interpreted it. It's the flag. What if no one can hear you scream? What if the program has closed standard out and standard error?
FEEF. You're forgetting infinite loop.
Right. EBFE is an instruction, otherwise known as jump -1. Otherwise, you actually don't even have to do that. You can do this sort of thing. I'll give you a hint. So let's, instead of exiting, let's make this guy hang. We say foo, and here we do jump foo. Okay? We'll assemble it. Oops, object copy. What? No, this should be fine.
Exit it first.
No. Oh, it's the wrong shellcode. Sorry. Okay, what are we doing? We are and here we do jump and. Thank you. AS, brilliant. Object copy, brilliant. Cat, it hung. So how can we use that? First of all, Zach's right. This tells us, hey, our shellcode is being executed. That's one very important thing. The other important thing, it tells us, hey, our shellcode got to the very end. This gives you one bit of information. So you could write a shellcode.
You could also append it with a not with a shellcode, like 2. If you wanted to keep that to determine how many bytes of shellcode you can execute.
Yes, there's a number of things you can do to play with this. One very important one is it's not just 1 byte. Think of other ways that programs can communicate with the outside world. Right? So I'll give you one hint. The value in exit. Even if standard in and standard out is closed, you can exit with a return code. So what can you do with that? That gives you 1 byte of output. This gives you 1 bit. You can already do a lot. So, lots of various situations where you might have to do some crazy stuff. Homework 6, is it up? Connor, where are you?
Yes, in 1 second.
Homework 6 will be up in 1 second. It's up now. So, you're all going to become shellcoding pros. 3 points per challenge. This means 24 challenges. The first 6 are almost free. I think with the shell code we wrote today, you can solve the first 6.
The first 4 are free.
The first 4 are free.
The next 2 almost free.
The next 2 are almost free. I honestly don't remember anymore. But you will see. I mean, they're all have walkthroughs. These first 3 levels that are up right now. The next, some of the really far away levels might not have walkthroughs.
How many challenges are there?
There will be something like 36, I think.
Including teaching challenges?
Including
Teaching challenges are still worth 3 points, or?
they're still worth 3 points.
So wait, is that 3 batches? Like 12 batches of 3?
My internet went down too. The internet's out, so either might be free.
Oh, is that your
What?
recording thing? I don't think so.
Oh, wait, no.
Telling you that it didn't work?
The system will turn off momentarily. Okay. So that is assuming anything has a walkthrough down. I have to check this one. Anyways, the first 3 are fully ready and fully up. Remaining ones we can push tonight. Depending on how much sleep I can forego. And have fun, enjoy. This is an amazing lost art or dying art, and you will soon be one of the elite who can shellcode. Good luck. Oh, hold on. Someone asked me about fall break and if you'll have a reduced challenge set. So fall break will be within the homework that's next week, right? All right, so I'll probably do something reduced. Definitely, probably no race to the finish. Easy set of or a smaller set of challenges to finish, something like that.
So how you like cat your program into the challenge?
You just cat and redirect, cat and then pipe through the challenge.
How about it? Work.
You can echo it, but then you have to echo all of the, like, I could do echo, shax48, -x, AD, and so on. It's a bit of pain.
What's this?
That is this data.
Oh, okay.
Yeah, so do cat.
Okay.
Yeah. All right. What's up?
All right, so my only question was, so I literally ran the